We know that organisations, moving away from the purely technical, organisations, certainly in the Western world, have very fixed temporal triggers. They use years, months, weeks, days, hours, minutes, seconds. These are shared common notions in a large part of the world's societies, and we use those common notions in order to coordinate activities, certainly within organisations. But there are scale problems, and there are amazing, simple things like the fact that a different number of days in a month do cause organisational failures, and the number of weeks in a month, as these scales do not perfectly match one to another. We recognise the large number of common phenomena, even if we're looking at things that occurred every year, all the way down to things that are scheduling the activities on a shared bus on a multi. Periodicity, things are repetitive. Things have deadlines that need to be met. We want to be able to schedule resources because wherever we are, there isn't enough resource to do what we want to do. There's no temporal validity. Our systems are dynamic, there are data in that system, and that data runs out of its validity. The properties that we found influenced what we wanted in our framework was issues of dynamics in the central feature in describing a system. Not structure in terms of physical structure in the hierarchy, but dynamics. Events are a key way of specifying behaviour. And then once you've got this idea of an event, of an instantaneous or atomic element of a behaviour, then you want to compose those in things like put them into an order, or define them to be simultaneous or separate, immediate, precedence relationships, causal relationships, observational relationships over events. We also know that to cause events to occur, we need resources in the system, so we have the idea of activities that take time and require resources. So events and activities are going to be the two main drivers for describing how systems behave. Clocks, abstract clocks, are useful. Also, we can't deny the fact that sometimes, or most of the time, we want to talk about discrete time, but particularly when we're interacting with the environment in some sort of control system, we also need notions that are more commonly expressed in continuous time. So hybrid, elements of hybrid time we can't ignore. And the final one is the notion I mentioned already of tolerance, accuracy, non-determinacy. Being able to specify some tolerance when we talk about time, just as we often talk about tolerance when we talk about physical things. So this is 3 kilometres plus or minus so many metres, etc. So let's get on to the framework itself. So I'm just going to go through a number of slides, some of the features that we actually put into this time-bound framework. First, we use time itself to separate concerns. So a system is primarily described in terms of a finite set of partially ordered time bands. So leave out the partially ordered bit, that's just needed for completeness and certain descriptions, but most of the time, and certainly with the examples I use, we're talking about a strict sort of hierarchy of time bands. So we'll have a number of time bands, and the primary characteristic of a time band is its granularity. There's a second characteristic, so I'll mention in a moment, called precision, but primary characteristic is granularity. So we might have an hour band or a millisecond band. But we also may define the time base by some other physical phenomenon. So in an engine controller, we might have the rotation of a crankshaft to be the definition of that time band. So we have a set of time bands in our system, and we have this separation so that if you're in a particular time band, the world that's slower, that's moving slower in a higher time band, as we say, we can assume to be essentially static. So while you're doing something in this time band, things in the slower time band can be considered to be static. Whereas things in the faster time band can be considered to be instantaneous. So we have a nice spread. The world up there is static, the world down there is instantaneous. example, when you're giving a lecture on a course in a university, then while you're giving a lecture, you assume that the curriculum is fixed. We know that curriculum changes from year to year, but in the middle of the lecture, you really don't want to take on board curriculum changes. So the curriculum is fixed. And when you press a button to move to the next slide, then that's instantaneous from this description. I can assume that that slide change is instantaneous. Okay, when I go down to a technical band, then clearly it's not instantaneous. There's all sorts of computation and scheduling going on down there in order to make that slide change work. But for this level of description, it's instantaneous. So we've got a partially ordered set of bands. And within the bands, we may describe continuous features and discrete behaviours. So here, there's three time bands, and there's a granularity between those points. So long spaces, small spaces, very small spaces. Just use this example a bit later. But those are time bands. Within time bands, two primary descriptions of behaviour are activities and events. Events being instantaneous, atomic, and activities taking time and requiring some resources. The case studies we've done drives us increasingly to the view that the initial description of any behaviour is usefully given as an event. Describe systems in terms of instantaneous events and then clarify what you mean by that by adding structure at a lower level of time band where you can add some temporality to that instantaneous event. A little straight off the middle. So events that are in a one band, we say map to activities in another band. So here's an event, cut at the timeline in that higher time band, but we map it to an activity in a lower time band that has duration, that has a number of ticks of this duration. And it's hierarchical. We might take an event, this is a behaviour composed of a large number of events, take an event there, and it maps to perhaps an activity at a lower time band. And the key to the constraint here is that that duration must be less than what's deemed to be the precision of this time band. So the time band at the top level has a precision which is an understanding of the constraint that's implied by saying something is instantaneous. So we have this duality. At one level, we have an abstraction of something that's instantaneous, but when it becomes more concrete, then there's a constraint on the duration of that activity. And that constraint is defined by the band up here, where the event was. And it's the precision of that band. So there's two major parameters for a band, the granularity and the precision. Granularity is the ticks of that band. The precision is what I mean, the tolerances I mean by something that's going to be instantaneous. So progressing, clocks are useful, abstract clocks, the idea of time in like 10 o'clock, 11 o'clock, 12 o'clock in the hour band. So the precision will mean what you mean by 12 o'clock. You mean 12 o'clock plus or minus the precision of that band. So if you're meeting somebody at 12 o'clock, you have a natural tolerance, which might be cultural. In Portugal, it's plus or minus 15 minutes. In most countries, it's a bit tighter. Yes, it's always so as I pictured before, we have the idea of events. So clock events are no different from any other events in this formalism, but they're just deemed to be regular by definition. We can have simultaneous events. That's useful. So this talk started at 10 o'clock. So there was an event, which was the start of the talk, and there was an event which was 10 o'clock, and they were deemed to be simultaneous. Of course, what we mean is that they were in the tolerance. So we started within 5 minutes, and therefore that was deemed to be simultaneous. We can also have simultaneous and precedence, what might be called immediate.